in the very first lecture, in the motivational part for the functional analysis, we discussed that in functional analysis we are attempting to generalize analysis on R, on the real line, or on Rn, by replacing Rn with more general structures. And then the aim is to make analysis on these more general structures, and in particular study the set of functions, or what is the analog of functions on these more general spaces. So far in the course we have studied a lot of spaces, normed spaces, metric spaces, inner product spaces, and so on. It's time to go for the generalization of functions. So the topic of today's lecture is linear operators. So let us start with the definition. Let E and F be normed linear spaces. And now we will consider a mapping from E to F and we call this mapping a linear operator well, if it's linear, which means that A of x plus y equals to A of x plus A of y, which is the additivity. And E of alpha x equals to alpha of x. This property is called homogeneity. And if these two properties holds for any x and y from E and any alpha from the set of scalars. We are rather not interested in all linear operators. We are interested in kind of very nice linear operators. Let's write down a few more definitions specifying the properties of linear operators. A linear operator is said to be first bounded, if there exists a constant such that a norm of Ax, this is the norm in F, is less than or equal to constant times the norm of x, this norm is in E, for every x from E. The second property we are interested in is continuity. We will call a linear operator continuous at some point x naught in E if for every sequence xn in E such that the norm of the difference xn minus x naught tends to 0, which means in particular that xn converges to x naught, we have axn minus ax naught. The norm of this tends to 0 as well. Yeah, as you might notice, sometimes I'm writing just a of x, and sometimes I'm writing a parentheses of x. This means exactly the same thing. Sometimes when we have a sum here, it's more convenient to write these parentheses. When there is only one element, we can just drop them out. Okay, this is a continuity at a point, and naturally we will call a linear operator continuous if it is continuous at every point. Now let us consider an example which shows that the realm of linear operators is very different from the reality of the usual functions on the real line. So, example. Let us consider a linear operator A from R to R, well, which is just a usual function, which is, well, the identity. So A of x equals to x. So if we will think about this linear operator as a function, then the graph of this function looks like this one. And as a function, well, first of all, it is continuous on R as a function, and as a function, it is unbounded. So the values of the function can grow arbitrarily large. So as a function, A is unbounded. But as an operator, it is bounded. But the absolute value of A of x, which is in R, means the norm of x, the norm of AX, just equal to the norm of x over here. So it is bounded with the constant c equal to 1. So linear operators and functions on array are very different things. Well, again, from the usual calculus, you can construct a function which is continuous at some points and discontinuous at some other points. This is not the case when we speak about the linear operators. A linear operator A from E to F. Well, E and F will be the non-linear spaces throughout the lecture, or even throughout several of the lectures. A linear operator is continuous at continuous on E if and only if A is continuous at some point. Well, if and only if statement, in this if and only if statement, we are only interested in one part. Of course, if the operator is continuous, it is continuous at every point, by definition. The converse is rather more interesting. So if an operator continues at a single point, then it is continuous on the whole space. So let's prove it. Let A be continuous at x naught in E. And let x be any point in E such that x does not equal to x naught. So we suppose that A is continuous at a point x naught and take any other point of this space. So we want to show that A is continuous at this point x. So by definition, we need to take a sequence converging to x and show that A of that sequence converges to A of x. So let xn be a sequence from E such that xn converges to x. As a side note, note that then the sequence yn equals to xn minus x plus x naught converges to x naught. Just as a side note. So this one then converges to 0, and so the whole sequence converges to x naught. Let us now consider A of xn minus A of x in F. So we want to show that this norm tends to 0 as n tends to infinity. Let me add and subtract A of x naught. Now I will use the linearity of A to bring all these three terms together. But this is nothing but yn, this one. And we know that yn converges to x naught and A is continuous at x naught. So by definition, this tends to 0. And we're done. So we have just proved that if a linear operator continues at some point, then it is continuous everywhere. An equivalent statement, of course, is that if a linear operator continues at 0, then it is continuous everywhere, which is, well, the same stuff. Which is fairly surprising. So the second proposition is, well, not less surprising. So the second proposition will tell us that boundedness and continuity is exactly the same thing. A linear operator is bounded if and only if it is continuous. Let's prove this. Let A be bounded. We want to prove that it is continuous. It's sufficient to prove that it's continuous at some point. So let's fix a point and consider a sequence converging to that point. And let's now consider the norm of the difference. AXN minus AX naught in F. So the operator A is linear, so we can write it like this. A of xn minus x naught. And A is also bounded. So this is less than or equal to constant times xn minus x naught in E. But xn converges to x naught. So this expression tends to 0. And therefore, A is continuous. Let's now prove the second part. A be continuous. And let us also suppose to the contrary that A is not bounded. That is, for every n from n, there exists xn from E such that the norm of Axn in F greater than n times the norm of xn in E. Well, first of all, let us know that we can assume that xn are not zeros, because otherwise this is a trivial statement, more or less trivial. Well, since I need the fact that xn is not zero, you may probably guess that I'm about to divide by the norm of x. So set yn to be xn over n over the norm of xn. Well, it is easy to see that this sequence yn tends to 0. Let us now compute A of this sequence. In the denominator we have a constant, so we can factor it out since A is linear, to have Axn over n norm xn. Hence, the norm in E, the norm of Ayn in E in F is greater than 1. So the sequence yn tends to 0, but the norm of Ayn does not, which means that A is not continuous. So we suppose that A is not bounded and ended up with the fact that A is not continuous. So this contradiction proves that A is bounded. Now I will give you one interesting exercise. Let A from E to F be a linear operator. If E is finite dimensional, then this operator is bounded. That is, any operator defined on a finite dimensional, any linear operator defined on a finite dimensional non-linear space is bounded or equivalently continuous. So let us restrict our attention to bounded operators only. So if A is a bounded operator, from the definition of the boundedness, we can say that this set M, and here I will take the norm of AX and divide it by the norm of X for every X from E, and of course we want that it does not equal to 0. So this is a set of numbers, so numerical set. This set is bounded from above by a constant c from the definition of the bounded linear operator. And let us now define the norm of a linear operator as a supremum over this set. A norm of a linear operator as an operator from E to E to F will be a supremum over M, or in other words, supremum of these expressions. Such that x is in E and x is not 0. This quantity is called the norm of a linear operator. Okay, let us now prove a proposition which provides a various different formulas to compute the norm of a linear operator. Proposition. Let A be a linear operator. Then the norm of A can be also calculated as a supremum of the norm of E of x in F over all x's from E such that the norm of x is less than 1. Or even it can be computed as a supremum of the same norms over all x's such that the norm of x is 1. So in the definition of the norm, we computed supremum over the whole space except the 0 element. This formula tells us that the norm is attained on the unit ball, and this formula tells us that it is even attained on the unit sphere of the space E. We have by definition, the norm of A equals to supremum of this expression over all non-zero elements of E. By the properties of the norm and linearity of A, I can write it like this, as a norm of A of x over the norm of x. Supremum is still over all non-zero elements. Now, I will estimate it from above by supremum of A of y for all y from E with norm less than or equal to 1. Or even, yeah, it's even simpler, just equal to 1. because the norm of this element equals to 1. The norm of this element is 1. So I estimate it from above by the supremum over all elements of the norm 1. Then I can write it like this. Supremum A of y norm f over the norm of y, which is 1. So over here we're taking supremum over the sphere, which is less than or equal to then supremum over the whole space, which is the norm of A. So we have proved that the norm equals to this one. So we started from the norm of A and ended up with the norm of A. So we proved that the norm equals to this expression. Now we want to prove the first equality. So first of all, let us note that for every x in E with the norm less than or equal to 1, we have the norm of AX in F is less than or equal to the norm of A times the norm of X by the definition of the norm. But the norm of X in E is less than 1. So this is less than or equal to the norm of A. Now, by the equality we have just proved, we have that the norm of A is greater than or equal to the norm of AX by this one. So we can take supremum over all x's from E with the norm less than or equal to 1. Here we're taking the supremum over the ball. So if we take the supremum over the sphere, it cannot be larger. So it is greater than or equal to supremum of the same expression over all x's of norm 1. But we have just proved that this expression equals to the norm. And we're done. Let us now consider a couple of examples of linear operators. Our first example is the Fredholm integral operator. Consider an operator A of x that will be a function of t as an integral from a to b for every continuous function x. So this operator is defined on a space of continuous functions. If we also assume that that function of two variables, k, of t and s, which is called the kernel of the operator, if we assume that this function is continuous as well, so we want that the integral makes sense, with the function k of two variables be continuous on AB times AB. Under this assumption on k, we deduce that not only A is defined on this space on the space of continuous functions on AB, but the output the value of A is also in this space. By linearity of the integral, this operator A is linear. So indeed, if you, instead of x, you will write x plus y, then you can split it into parts. So it is easy to see that it's linear. Hence the operator is linear. Let us first show that the operator A is bounded. I forgot to say from the very beginning that we consider this space CAB with the uniform norm equipped. With the uniform norm. The norm of AX in this uniform norm, the uniform norm of AX, equals to the maximum over all T just use the definition of the norm. Now I will bring the absolute value inside the integral. So this will estimate this expression from above. So this is less than or equal to the maximum And now I will estimate this absolute value of x of s by the norm of x. By definition of the boundedness, the operator A is bounded. A is bounded. And the norm of A is less than or equal to this constant. Let us further prove that, in fact, the norm of the operator equals to this constant. So what do we have over here? So if we look at the function which stays under the maximum, so this function, it is a function of t, and k is continuous, then we take an integral. What we have here is a function defined on the interval a, b, and this function is continuous on AB, which means that it attains its maximum. So there exists a point t0 from the interval AB such that the value of this function at t0 equals to exactly this maximum. So let's write this down. Now I will take an arbitrary epsilon greater than 0 and consider very specific functions. I will call them x epsilon of s, x epsilon of s, which will be k at t0 s over epsilon plus k of t0 s. So for any s from AB on the interval AB, we consider these functions for every fixed epsilon. X epsilon is a continuous function on AB. And that is just by the definition, and since k is continuous in both variables. Now let's compute the value of A at the functions x epsilon. So first of all, let us notice that the norm of x epsilon is less than 1. Now we will use the formulas for the norm of the operator which we have just proved. The norm of A equals to supremum of all AX for all x from CAB such that the norm of x in CAB is less than or equal to 1. And the norm of x epsilon is less than or equal to 1, which means that this is greater than or equal to the norm of ax epsilon. It is ax epsilon of t supremum over all t. So if I will take just the value at t0, then I will make it not larger. And if I drop off the absolute value, it will be not larger as well. Now let's use the formula, the definition of A and the definition of x epsilon, and see what we get. What I will do now, I will add and subtract epsilon to this term. And now I will divide it through to get an integral from a to b that will be the first term minus epsilon which is less than or equal to, I will keep the first term, what we have here under the integral, the integrand, is less than or equal to 1. So I can make it larger. So I will replace this one by 1. To make the whole expression smaller, and then I need to integrate 1 from a to b, so I need to multiply by b minus a. And let me also recall that this expression, due to the choice of t0, is nothing but the constant which we want to prove the norm equal to. So we have estimated the norm from below by this expression minus epsilon times constant for every epsilon greater than 0. Which means that the norm of the operator equals to this expression. Let us consider one more operator. Since we already considered the integral operator, let us take as a second example a differentiation operator. We want to consider an operator which takes a function and returns its derivative. So first of all, we cannot just consider it in the space of continuous functions, because we want the functions for which the derivative exists. So let us consider an operator from C1, 0, 1 to C0, 1. So this is the space of continuously continuously differentiable functions. And I define an operator a of x equals to x prime, just the derivative of, let's rather go with the fancy one, of t equals to dx dt. And of t as well. Well, as in the previous example, we consider this space C01 with the uniform norm. And also we equip C1, which is a subspace of C, also with the uniform norm. Let us show that in this case, the differentiation operator is unbounded. So let us consider xn of t, which is sine of phi n t. So these functions are clearly continuous for every n, and the norm of any xn is 1. Let us now compute AXN, so the derivatives. But AXN of t equals to pi n cosine pi n t. So the norm of AXN equals to pi n. So the operator A is unbounded. Let me say that as an operator from C1 with the uniform norm to C with the uniform norm. But the uniform norm for C1 is not a very good one. So in particular, with this norm C1, so this space C1 with the uniform norm is not complete. There is a nice norm on C1 in which in particular C1 is complete. So let us take C1 with the other norm. So the point is that this is the space of one's differentiable functions. But in the definition of the norm, we do not use any information about the derivative. It turned out that if we will do this, so if we define the norm as the norm of x itself and plus the norm of derivative of x, then it is also a norm, and this norm, as it turned out, much nicer. Let me call this norm x. Let me write 3 bars over here. Let us now consider this operator A of differentiation from C1 with this new norm to C with the usual norm. Well, the operator is still linear. There is nothing specially in here. But now this operator is bounded. We have the norm of AX equals to the uniform norm of x prime, the derivative, which is less than or equal to the norm of x plus the norm of x prime. So I just added this term. But this is the norm on this new norm on C1. So A is bounded. As a very important conclusion of this, so the boundedness of an operator depend not just on domain and codomain, which is not a surprise, but it is also depend on the norms. We already know that it is bounded, and the norm of this operator is less than or equal to 1 due to this one. Now let's take xn to be sine of pnt over pn. Then the axn is then cosine pi nt. That is the norm of axn is 1. On the other hand, the norm of xn, the new norm, in C1 equals to the norm of x plus the norm of its derivative, which is 1 over pi on n plus 1. So this norm is exactly this norm. The norm of A is greater than or equal to supremum over all n. The norm axn over the norm of xn, which is 1 over pi n plus 1, or in other words, pi n over 1 plus pi n, which tends to 1 as n tends to infinity. So from over here we have that the norm is less than 1, and here we have that the norm is greater than or equal to a sequence which tends to 1, which means that the norm of this operator is 1.